Okay, well, let me welcome you to this 8th lecture of our course. This lecture marks the beginning of the second part of the course. So far, aside from review, we have been focusing on online play algorithms. With today's lectures, we're going to start focusing on online training algorithms. And in today's lecture, we're going to talk about neural networks and parametric approximation architectures. And we will also look on how these are used in various reinforcement learning contexts. Okay, so here's the outline, a few things in the way of review. Then we're going to talk about parametric approximation architectures, including neural networks, as well as feature-based architectures. And we're going to rely on videos from previous offerings of the course. Today is going to be a long lecture, and it's going to involve several clips. After we introduce parametric architectures, we're going to talk about how we train them, the optimization algorithms and the optimization formulations that we use for the training. Then we're going to talk about specialized optimization algorithms of the gradient type, but incremental, and I'll explain what that is. Not the usual gradient methods, they're incremental gradient methods, which have been very successful in the context of training of architectures and particularly neural networks. Then we're going to say a few things more specific to neural networks and their properties. And then we're going to discuss how neural networks can be used within finite horizon dynamic programming contexts. In future lectures, we're going to focus on infinite horizon context and the policy iteration method in particular. However, today we're going to focus on finite horizon context. So, some review. Let's look at the AlphaZero MPC, model predictive control model, that has been our guide for the development of theory and algorithms so far. Remember that we made a distinction between online play algorithms and offline training algorithms. Now, the online play algorithm is what you see here in blue. It involves look-ahead minimization for one or more than one stages, followed optionally by truncated rollout, look ahead with a specific policy, the base policy. And then at the end, if we have not finished, we take a cost function approximation. We add a cost function approximation that encodes the quality of the state at this stage of the look ahead. The very first step of look-ahead minimization is also related to Newton's method. It's a Newton step. And we made an interpretation which we emphasized that the first minimization is a Newton step for solving Bellman's equation, and the remainder is preparation for the Newton step, setting up and improving the starting point for the Newton step. Now, this preparation here involves interaction with the offline training algorithm. The offline training algorithm provides the terminal cost approximation, and optionally, if there is this middle portion, it provides the base policy for implementing this truncated rollout. So most of what we have discussed has to do with the blue part. And now we're going to talk about how we construct terminal cost approximations and base policies from data. This is called a value network sometimes, and this is called a policy network, usually when neural networks are involved. So let me get to you a broad outline of what we've done. We started with 4 overview lectures, which were intended to give you the big picture and to get you started with your term paper or mini project. And we focused on online play algorithms. And there were several of those that we discussed, rollout algorithms and their variations in finite horizon, and also as the very first iteration of the fundamental policy iteration method for infinite horizon problems. Now, for deterministic problems, there are several, and for some stochastic problems, there are several variations. Fortified rollout to ensure cost improvement, simplified, minimization, for constraint problems, for minimax problems. And one particular type of simplified rollout is the multi-agent rollout algorithm that makes approximation in value space and look-ahead minimization possible for problems that involve controls with multiple components corresponding to different agents. We also emphasize the importance of online replanning for problems with changing parameters, a changing model, and the context of adaptive control. And we discussed also model predictive control and related issues to it, special problems. So that's what we've done. And this is where we're going. We're going towards offline training algorithms, and we're going to have 5 lectures on this topic. And the 5 lectures correspond to these bullets that I have here. We're going to cover in some depth and in some detail approximation of values and policies with neural networks and other architectures. This is today's lecture. The next lecture is going to focus on infinite horizon problems. The algorithm of policy iteration and other algorithms focus a little bit more on theory, error bounds, lay the ground for considering approximations, policy iteration, approximate policy iteration algorithms, Q-learning. For the 3rd lecture, then the first 3 lectures deal with approximation, mostly with approximation of cost functions. The 4th lecture is going to deal with approximation in policy space and algorithms called policy gradient methods and other related methods for training policies. Finally, we're going to talk about aggregation, which is approximation in value space, but of a special type, but has special properties, and we're going to devote 1 lecture to that. Now, if you compare what we're going to do with the 2021 course, it's going to be pretty similar. So if you want to read ahead or view ahead, you may look at the slides and the video clips from the previous, from the 2021 course. So what I'm going to do now is do a review of approximation value space and how everything fits with that we're going to discuss today fits in it. And I'm going to use the video from from the previous offering, the 2021. Okay, here we go, and I will stop at various strategic points to take questions. The general context, the general structure of approximation in value space. You've seen this figure before. This relates to 1-step look ahead at a given state xk. We select control by minimizing this expression involving the first step and the future as approximated by some approximate cost function, j tilde k plus 1. And there are also 2 other types of approximation, the 3 approximations. Approximation of the minimization here, and approximation of the computation of the expected value here. And these 3 approximations can be done reasonably independently from each other. And we have discussed several topics in each one of these types of approximation. For example, we've discussed the multi-agent minimization, which is an approximate form of the true minimization. we have discussed making approximations in the calculation of expected values through certainty equivalence, adaptive simulation, Monte Carlo tree search. And we have also discussed, spent a lot of time discussing various methods for approximation of these J tilde functions. Problem approximation is one of these approaches. We spend a lot of time on rollout. In this special case, model predictive control. And today, we're going to focus on this pink colored topics of parametric approximation and neural networks. Similar things hold for multi-step look ahead. Today, we're going to focus primarily on one-step look ahead, but almost everything goes through for multi-step look ahead situations. So let's talk about parametric approximation architectures in general. There are two types of things that we want to approximate in reinforcement learning. One is to approximate costs in either a finite or an infinite horizon setting. In particular, we may want, in a finite horizon setting, we may want to approximate the optimal cost function at stage k or the optimal Q function at stage k. In the case of an infinite horizon, there's no dependence of the optimal cost on the stage k, so there's only one function, optimal cost function, to approximate, and we may be interested in approximating that, or the corresponding Q function. We're also interested in approximating cost functions of policies, like in rollout, for example. So this deals with approximation of an optimal cost function. This deals with approximation of a specific policy, either in a finite horizon setting or in an infinite horizon setting. We're also interested in approximating Q functions of a policy in a finite horizon or an infinite horizon setting. So all of this is cost approximation. The other thing that we wanted to approximate is policies. Again, in either finite or infinite horizon settings. We may want to approximate optimal policies, or we may want to approximate given policies. So this would be, the approximations would be mappings that map a state into a cost that's approximately equal to this or that or this or that. So all of this deals with approximations, and we have several ways of doing these approximations. However, we are going to focus on parametric approximations. So a target function J is going to be approximated by another function, J tilde, that depends on the state, but also depends on a parameter. So this J tilde is a member of a parametric class of functions, parameterized by a parameter vector that may have many components, right? It's generally a vector of scalar components. And similarly for policies, we want to approximate mu with a member from a parametric class, functions that depend on X, but also involve a certain parameter. And by choosing the parameter, we can obtain different approximations. And the idea is to choose the parameter in some kind of optimal way or semi-optimal way that matches data that we have about this target function and this target policy. Now, an example is, we're going to give several examples, but one example is neural networks. And in this case, R is the set of weights of the neural network. We're going to discuss neural networks and weights shortly, but basically this R is a big, big vector that involves various parameters of the neural network that encode the various layers of the network. And then the problem becomes determining the set of weights so that the neural network provides approximations that are close to the target cost function or the target policy. So this is the general objective, and this corresponds to a value network that we mentioned in the case of alpha 0, for example. This corresponds to a policy network, constructing a policy network. Let's see how this parametric approximation works for the case of costs. We have a certain target cost function, be it an optimal cost function or be it a cost function of a policy, and we obtain training data from that target cost function, which are state control pairs. There are many of those, Q in number. These are selected states from the state space, and these are the corresponding cost function values, which somehow we compute, perhaps with some error. But for the moment, we're going to neglect the errors, and let's say that we compute exactly these cost functions. Similar things hold if there are error terms here. So we have the target cost function, we have training data that we collect somehow, and then we also have a family of approximating functions, an approximating architecture. This family is parameterized by a parameter vector, like the weights of a neural network. And for every parameter R, we obtain an approximating function, and we want to find R so that this function here matches well the training data. In other words, if you compare the training data with what the approximating function tells you that the cost is, the error is small. Like, for example, the sum of the squares of the errors is minimized or almost minimized. So this is the training problem, finding R. And this can be done with an optimization type of algorithm. It's almost always done this way. Specialized optimization software based, for example, on gradient type methods. We're going to discuss these methods shortly. And there are also other possibilities like special least squares methods. We're going to say a few things about those as well. So that's the general structure of parametric cost approximation: a target function, training data, a family of functions, choosing an element from the family so that there is good match between this and that. Are there any questions here? Okay, so let's go into the other type of parametric approximation, policy approximation. Now, if the control, this is a little different because costs are scalars, right? Whereas policies are controls, involve controls from a control space. Now, if the control has continuous real valued components, like, for example, it's the vector of positions and velocities, three-dimensional position and velocity of an airplane, okay? Has 6 real valued components. In that case of continuous components, continuous controls, the training is pretty similar to the cost function case. It's scalars in one case. In the other case, it is multiple scalars, but the idea is similar. Basically, you replicate the computations for a single scalar to obtain approximations for a whole vector of components. On the other hand, if the control comes from a finite control space, can only take a finite number of values, then we need to modify the approach of approximation a little bit. And there's an interesting analogy here, an interesting resemblance, relation between the finding an approximating policy and building a classifier. Okay. What is a classifier? It's a very well-known type of algorithm, software from machine learning, whereby we have a population of objects and we have a finite set of categories, and we want to classify objects from this population into one of these categories. Look at it and then decide which category it belongs to. Like you have okay, digitized images of apples and oranges, and you feed them to the computer, and the classifier will classify it as an apple or an orange, okay? Now, if you think about it, a policy, in the case where you have a finite control space, is a classifier. Basically, it maps X, the states, into some category. The categories are these M's. So the category 1 are the states that belong to category 1 are the ones for which the control is equal to U1, and so on. So basically, there's one-to-one identification of policies in this finite control space and classifiers. Now, classification, or pattern recognition, as it's otherwise known, is an old technique. Dates back quite a few decades. And one of the first and most fundamental algorithms in machine learning. And therefore, it makes sense to use this classification experience and algorithms in the context of approximation in policy space. And the way this will work is shown here in this picture. We have a target policy, mu, and we collect training data from it. State control pairs, a collection of states, x1 up to xq, and the corresponding controls from the target policy. This target policy may be, for example, the rollout policy corresponding to a given base policy. We have ways to calculate the values of the rollout policy, and when you do that for many states, we obtain training data. And this training data is fed into a classifier which assigns state X to control U. And there's only a finite number of U's here, or categories. And they depend on a parameter. Now, many, not all, but many classifiers actually do not produce a single category to assign to any given state. But instead, given a state, they produce probabilities, a probability distribution of the different categories. So given X and given R, the classifier gives the probability that this state belongs to category 1, or this object belongs to category 1, and the other probabilities that the state belongs to category 2, and so on up to M. Now, in the context of policies, this type of object is what's called a randomized policy, assigns to a state a probability distribution over controls to apply. Now, you may recall that in AlphaZero produces a sequence of players, and these players are randomized policies. For a given chess position, they give the probability distribution of play of various moves, with desirable moves having higher probability and pretty bad moves having probability essentially 0. So this idea of generating randomized policies through training is central in AlphaZero. It's common in reinforcement learning, and it's to a great extent due to the fact that a lot of classifiers prefer to produce probability distributions at the output rather than a single control. Now, once you have a probability distribution, you can obtain a single control by using a max operation. In other words, you assign to state X a control that has the maximum probability out of the probability distribution produced by the classifier. So all of this training can be done with classification software. Some of them use neural networks, some of them do not. Some they have a great variety of classification software, and many of those are useful in the reinforcement learning context if the number of controls is finite, okay? In the case where the controls components are continuous, then basically what applies for costs also applies for controls. Let me also mention that there is a reason why classifiers produce probability distributions. And this has to do with algorithms. There are algorithms that deal better with continuous outputs rather than discrete outputs. But this will not concern us because we're not going to deal with the problem of classification and the algorithms for doing that in this course. We're going to leave parametric policy approximation at about this stage, and we're going to focus on cost function approximation in what follows in this lecture. Are there any questions? I'm stopping the video to take questions. Do you have some questions? Okay, we'll keep on going. Okay, so let me say a few general things about cost function parametric approximation. As I mentioned earlier, we select a class of functions that depends on a parameter vector that has m components, which you can change. They're tunable. These are scalar parameters that you can tune, and therefore change j tilde so as to match the training data from the target function. And by training the architecture, we mean that we apply an algorithm that chooses R, and this algorithm typically solves a regression type problem involving the sum of squared errors or something similar, errors between data and output of the approximating function. Now, it's useful to classify different parametric architectures according to their properties, and one property of this that is interesting is whether the approximating architecture is local or is it global. By local, a local approximation is one for which changing a single parameter, only one of those, affects j tilde only in a small part of the state space, locally. By contrast, a global type of approximation is one where changing a single weight here, a single parameter, affects the approximation over the entire state space. We'll see examples of both shortly. Another classification of architectures between linear and nonlinear. If j tilde is linear in R, nonlinear perhaps in X, but linear in R, then the architecture is called linear. And we'll see that we like linear architectures if they will work for us because the training is easier with linear architectures. But many architectures are nonlinear in R, including neural networks. They're highly nonlinear. Another very important concept. An architecture is called featured-based if it depends on X via a feature vector. Now, this is a vector of individual components called features that depend on X. And these features capture major characteristics of X. In other words, if I tell you X and I give you its feature vector, it provides you with a lot of information about the character of X, and is also useful in the context of of approximation because you can use phi of x as a substitute for x in effect. Okay, so back to feature-based architecture. It is called feature-based if J tilde depends on x through the feature vector. Okay, so this is general and nonlinear, but this is very specific. It uses, in place of x, it uses its feature vector, and j hat is some function. And the intuitive idea here is that this may be horribly complicated. It has very difficult and strange nonlinearities. On the other hand, these nonlinearities may be captured in these nonlinear features here. And if that's the case, then you can afford to use a j hat, which is relatively simple. Like, for example, linear in R. Linear in R, nonlinear in X, but through the features here, which capture the dominant nonlinearities of the target function. So now combining these two, what's a linear feature-based architecture? It is an architecture, an approximating function of this form here. Okay, this is what we use to approximate the target function. It depends on x through the features. These are the m features that constitute the feature vector. R is a vector of parameters, R1 up to Rm, and it is a linear weighted sum of the features, with weights being the parameters of the architecture. And you can write this as an inner product of this vector R with the vector of features phi of x. So that's a linear feature-based architecture, a very major class, a very important class of approximating architectures. If you know good features, this is a pretty good one, because like I said earlier, it can be trained relatively easily. And here is a picture of an illustration of a linear feature-based architecture. Given a state, we pass it through a feature extraction mapping that calculates the feature vector, these m numbers corresponding to the state x. Now, these m numbers, the feature vector, are fed into a linear mapping involving this parameter vector R, and out comes this expression, which approximates the target cost function. So that's all there is to it. A feature extraction mapping to give you the feature vector, and then linear weighting of the features to give you an approximation to the target cost function. So we're going to give now some examples of approximation architectures. Are there any questions?
I have a question. So R here is some weight we need to decide. So we don't know what R is, right?
We don't know what? I'm sorry, please repeat.
The value of R. The value of R is some unknown weight, right?
Yes, that's the object of training. We do it by using some kind of optimization training algorithm that we haven't discussed so far.
Okay.
So what is needed here is to have an expression for the feature vector, to be able to extract features. And then after that, this is the architecture, and then you have to train it to find the right values for R, so that this matches data that you have. Okay? Okay, so now I'm going to give you an example, a simple example of a linear feature-based architecture that is also local. Okay, so this is a piecewise constant function approximation. So we have the target function, and we want to approximate it with a piecewise constant function. So what does this mean? we partition the state space into some subsets within which the approximation is going to be constant. And we define as the Lth feature to be the indicator function of the Lth set, the indicator function of SL. So this is the feature here, what you see. It is either 1 or it is 0. So for L, it is like that, with a value of 1. Okay, this is the level 1. At a different set, this is another feature and another feature. Okay, and when you pick a particular X, then the feature extraction mapping picks out in which set of the partition here it belongs, and gives you the feature to be 1 or 0, okay? And then these features are multiplied with the weights. So the features are all 0, 1, okay? These are the features. And then when you multiply them with the weights, they provide a piecewise constant function. And by picking the weights appropriately, you can construct any piecewise linear approximation, which will approximate the target function. Now, this is a local architecture. Why is it local? Okay, remember that the local architecture is one in which if you change a single feature up or down, then this affects the approximation only on a small number of states, okay? Not in the entire state space, but in a relatively small subset of the state space. So if I change one weight here, I affect the function only within this set. That's why it's local. Are there any questions? Okay, so that's very simple, but it can be generalized to piecewise linear, for example, piecewise quadratic type of function. Let's give an example of a global type of architecture that's very general. It's generic. It doesn't require that you know features. The features are generic. Suppose that X, the state, has n components. Let's consider these features, okay? N components. The first feature is just a constant, 1. Then there's n features that are just the components, the n components. And then there are additional n squared features that involve 2 components. Now, the corresponding linear architecture is this one here. This is the weight, the parameter that weighs this feature. Ri weighs the parameter of phi, and Rij is the parameter that weighs the cross product features. So that's the parameter vector. It has all these components. And by adjusting these components, we can build quadratic approximations of cost functions of states that have n components. This is a pretty general method, and sort of, we don't need to know special features. These are generic features. A generalization of that, instead of having quadratic polynomials here, we can have higher order polynomials, like cubic, okay? Polynomials in the components. Moreover, we can decide that we're going to set to 0 some of these weights and are going to look only at selected cross-product pairs. All of this is possible. It's a generalization of this quadratic architecture. Both of these are global architectures because if I change a single parameter, then this is going to affect every state, okay? It's going to affect the approximation of every state because it weighs directly the states over the entire space. an even more general architecture. Instead of having polynomials of state components, quadratic or higher order, we have polynomials of feature vectors of x. In other words, we construct for x an m-dimensional feature vector, and we construct a polynomial architecture that weighs the features. Now that's pretty general. And in fact, this is a valuable architecture in many ways because it combines both linear and quadratic features with problem-dependent features. Now, note also that a linear feature-based architecture is a special case of this. If you have, instead of a polynomial, the polynomial is linear, is first order. If you have a first order polynomial of features, that's exactly what a linear feature-based architecture is. Any questions here? Okay, so that's pretty general. At least for those, you don't need to know any special features of the problem. But there are a lot of problems where you do know some very valuable features that capture, to a significant extent, the nonlinearity of the target function that you want to approximate. For example, in chess, remember that in chess, the state is the board position. And then when a chess player looks at a board position, mentally extracts features from the position, important characteristics of the position. And these are, for example, the material balance, whether white or black has more material and how much more, whether the pieces have mobility, they can reach more squares or less squares, whether the king is safe, other strategic features like open files. All of this a chess player catalogs in his mind and mentally builds, evaluates the position. Well, actually, the position evaluator of a computer program does something similar. Extracts features that chess players find important and constructs a feature vector of the position and then weighs the features with parameters, usually linearly, and builds an evaluation of the position, a numerical value that gives, in some rough way, the probability of winning the game starting from that position. Every chess program before AlphaZero used features constructed heuristically from human experience. AlphaZero is different because it uses machine-generated features, as we will see, through the use of neural networks. But this is the kind of architecture that was used in the past and will continue to be useful in the future, perhaps in combination with ideas that are inherent in the neural network training of AlphaZero. Now, here's another example, which I've talked about in the past, Tetris, the game of Tetris, involving a wall of blocks and objects that are randomly generated, that are falling from the top, and you have to fit them in. The wall goes up and down. If it reaches the top, then you lose the game and you stop accumulating points. And okay, I'm not going to repeat that, but a Tetris player, a human Tetris player, can look at a board position and can evaluate the position by using some features. And I talked a few lectures back about a 22-feature architecture, a linear feature-based architecture with 22 features that involve important characteristics of the state, like the height of the different columns of the wall, the relative height, the height differences, the maximum height of the wall, the number of holes inside the wall, and things like altogether, and a constant feature, altogether 22 features. And with these 22 features, the approximation architectures have been built that allow online play with approximation in value space to reach very, very high scoring numbers, impressively high scoring numbers. And so that's another example where the features are based on the characteristics of the problem. They are problem specific. Okay, here's another type of architecture that we're not. Just pausing for a second. Are there any questions? And I should add also that the number 22 for the Tetris program corresponds to a board with 10 columns, okay? If you had 20 columns, then that would be 42 features. So just to make that clear. But anyway, are there any questions so far? Okay, we'll keep on going. We're going to discuss a little bit late in the course. Suppose you want to construct a complicated approximation architecture, in particular, one that has different structure in different parts of the state space. So here we partition the state space into several subsets, and we construct a separate cost approximation in each subset. Perhaps in some of the subsets, the target function changes quite a bit. It's different, quite a bit different than in other parts of the state space. So you may want to have a different architecture to encode the characteristic of the, to represent the target function that sort of matches its character. So one possibility is to use a separate architecture on each set of the partition and do training on each set of the partition, perhaps with the communication between different parts of the approximations. And okay, we're going to talk about things like that later. But the point that I want to emphasize here is that it is possible to use a regular partition for the state space and approximate within each square of the grid, but that's not a good idea, generally speaking. Instead, it's a good idea to generate a partition by using features. This is called a feature-based architecture, partitioning. And suppose that you have a set of features that sort of represents the structure pretty well. It captures the characteristics of the target function that you want to approximate. Then you can do a regular partition in the space of features and map it back into an irregular partition of the state space. And the reason is the following. Basically, we want to partition the state space within with subsets within which the target function changes relatively little. Is kind of similar, has similar structure. So the rationale is the following. We want to group together states that have similar costs, similar structure of cost function. And we hypothesize that states with similar features should have similar costs. So it makes sense to partition the space of features into subsets that are sort of regularly spaced, and then map back the into subsets of the state space which have similar features and therefore, according to this hypothesis, similar costs. So that's the idea. It's a simple idea, but very effective if you want to do partitioning. Okay. So now what we have no knowledge of features or very little knowledge of features. That's where neural networks come into play. They allow us to bypass the need for handmade user-provided features. The neural network does everything, provides the features and trains the architecture simultaneously through a training process. This is the great role of neural networks in reinforcement learning. That's where that's their primary significance. They allow you to bypass the knowledge for features to construct cost architectures and also policy architectures. So here's the structure of a neural network. I'm going to go through this quickly because I'm going to start pretty soon the video lecture from the 2019 offering of the course, which is going to focus on this architecture almost exclusively. So remember that what we want in an approximation, in a cost approximation architecture, is given a state to obtain a cost approximation. And the way we do this with a neural network, a single layer neural network, a simpler version of a neural network, is we first take the state and we encode it into some function y sub x so that y sub x is shootable as input to the neural network. Also, y sub x may include some problem-specific features that we may know that they are valuable, but they are not enough by themselves to give a shootable architecture. We want these problem-specific features to supplement the neural network. All of this is done in this box here. We obtain y sub x, and then we pass it through a linear layer. That's a linear layer, which is basically a linear transformation involving a matrix A and a vector B. And these are the parameters of the linear layer. There are quite a few of them, right? Because this matrix potentially has a lot of weights, a lot of components. Now, here there is a vector coming out, perhaps of different dimension than this one, but this vector goes through nonlinearities, a layer of nonlinearities. Single input, single output, scalar input, scalar output from the nonlinearity. And this nonlinearity, of course, the output of the nonlinearity depends on x, but also depends on A and B, right? So let's call V the combined vector of the matrix A and the vector B. And at the output of the nonlinear layer, we see that we have m scalars that depend on x and a parameter vector. Now, we view this as features, m features of the state. And we combine these features linearly by taking inner product with a parameter vector r. These are linear weights that weigh the components of this feature vector. Okay, so out here is the weighted sum of these nonlinear features weighted by the components of the parameter r. And that's what the single layer neural network is. And that's how we use it for training. Now we're going to get back into this figure shortly, and I'm going to leave it here with just this introduction. So are there any questions before we go into the video?
I had a question regarding the target functions that we're using for training. I think you said at the beginning of the assumption that those are given, but in general, if we were going to try to figure those out from some of the methods we've seen in prior classes, those are all based on approximations, right? So we're using potentially approximations as our targets to do the training, and that error is just going to accumulate as far as I can tell. Is that the correct?
Well,
is that the situation that we're in?
Okay, so the target function may be easily obtainable or not so easily obtainable. The optimal cost function is harder to get samples from it, okay? On the other hand, from specific policies, you can get cost samples by running the policy and accumulating the cost through a simulator, okay? Or through some other calculation. Now, a simulator is not exact. It will have some simulation error. and it will involve some the training data may involve cost function errors, but this is all taken care into this least squares training process. In other words, the training process can work with training data that has cost errors in it. Of course, the smaller the errors, the better off we are, but we can deal with errors. It's generally harder to have access to training samples of the optimal cost function, but remember that in rollout and in policy iteration later, we can have samples of the cost of policies by simulating the policy. Does that answer your question?
Yeah, it does. Thank you. Also, I had a question about the last slide. Are those partitions themselves a result of some kind of separate optimization process, or are they just created through domain expertise usually?
Well, like I said, it's a good idea to use features to generate the partition. And features, generally speaking, require domain knowledge, right? Now it's possible to use a neural network to construct features and then construct a partition from these features. That's a possibility. But of course, that's pretty sophisticated stuff now, because you have to build a neural network first that will construct the features and then use the features for partitioning. So this can be simple, or it may not be so simple.
Okay, yeah, thank you.
Okay. Any other questions?
I have a question. Can you go to the next slide? So y of x is a vector that encodes the state, right? I guess I don't understand why we would do this linear transformation on y of x before mapping it into a higher dimensional space. Why not just feed y of x directly into the nonlinear layer?
Okay, there are several possible reasons for that. One is to be able to include some problem-specific features, okay?
Mm-hmm.
So this y would have, could be just x plus some additional features, however. The other there are other issues that have to do with scaling. We may want to scale y so that it falls within a certain bounded region, like scaling between 1 and -1, for example.
Okay.
So as to make the training process, to facilitate the training process. So there may be problem-specific and also algorithmic related issues associated with the construction of this y of x.
So it's kind of like a data conditioning layer where you're trying to put the vector into some correct format before feeding it into the nonlinear layer. Is that right?
Exactly. Yeah, exactly. It's in part a data conditioning type of process.
Okay, got it.
Okay, guys, now comes the critical moment in this lecture where I have to switch the video. So I'm going to try to do that with we go. Okay, this video is from 2019, and for a while it's a little dark, but it will improve shortly. But let me also pose to ask for questions. Are there any questions on? We heard several questions from 2021. Are there any questions that you have?
Professor?
Yeah.
I have a quick question. So regarding when we train the neural network, like in the last slides, the input seems to be one state. I was just wondering, like the input should be one state or all the states for training the offline training for the offline training.
It will be to approximate the cost function of all the states. However, we feed the neural network with samples of states. And these states, and the number of samples may be, like 1,000 or maybe 1,000,000 or whatever. But eventually we will obtain an approximation that applies to all states.
Okay, thank you. That makes sense.
Okay. Any other questions? Okay, I'm starting again. Obtained from the target function with a parametric architecture. So the first step is to collect data, to collect a set of state cost training pairs where, okay, there are Q of those. Q can be large, in the millions, okay? It's lots of data potentially. It may not be so big, but typically it is large. And it involves pairs of sample states. So this is the sample space, the sample states, the state space, and we sample it, okay, through some method that we're not going to get into in this course. And beta of S is just the value of the target cost plus perhaps some noise, okay? It's not quite the same. Depending on how we do the sampling, how do we collect the data, this may contain some noise. But still it captures the form of the target function. And we determine R, the parameter vector, by least squares minimization, okay? We fit the target function to the approximation architecture. We minimize the errors between these two, and we find R that minimize those errors. Okay, this is the basic form, but sometimes we add here a regularization term, a square term. This is the norm of R squared, a square term that depends on R, something like this. And this is to make this minimization a little bit better behaved, okay, to remove singularities of some sort. But there are also other reasons that have to do with more specific subjects to neural network, to approximation, like overfitting issues. Okay, this is important, but to simplify our presentation, we're not going to be adding it here. Okay, now here's the nice thing about linear feature-based architectures. The training can be done exactly. This training problem can be solved in closed form. How so? Well, if we have this linear feature-based architecture, then this function here this is linear in R, so this is quadratic in R. The cost function is quadratic in R. And quadratic problems can be solved in closed form. And what is this closed form? Well, here's the formula, okay? We're not going to be using this formula, but I'm going to explain it once. This is a vector formula. Remember, we are trying to find a vector of parameters. Okay, phi now is the feature vector at the sample xs, okay? So it's a vector like that, and it's multiplied with a scalar. So this sum here is a vector. And how about this thing? Let's look at the inner product here. It is a vector, a column vector multiplying a row vector. So it is a matrix. This is an M by M matrix where M is the dimension of this R. And we add all those and we gain another matrix which we invert, okay? So this is the inverse of this matrix here, which consists of sum of matrices. Okay, so this is the exact formula. When we obtain this formula by plugging this in here, it's a quadratic minimization. We set the gradient of this to 0, the condition for optimality, and we solve the resulting linear equation, and it gives exactly this formula here. And the derivation is in your book, and I'm not going to go through it because it's not significant for our future purposes. Okay, so this is exact, but it still requires a lot of computation. Where is the computation here that bothers us potentially? The inverse, the inverse. The inverse bothers us, okay? When does it bother us? If we have a high dimensional matrix here, lots of features, let's say 10,000 features, and this becomes a 10,000 by 10,000 matrix. That's a significant inversion, okay? What else bothers us? How about this thing about 10 million data points? This means that we have to add 10 million matrices here before we can start thinking about inverting. And similarly, 10,000 vectors we have to add. So for a large number of features and large data set, this is in closed form, but it may not be the best. In practice, very often, instead of doing this solving this problem exactly, we solve it as if it were a nonlinear, as if it were a non-quadratic optimization problem. It would involve a nonlinear regression. So let's go now into nonlinear architectures and how we train them. And this also applies to linear architectures, if we so prefer to address them. Okay, now this problem here involves, again, potentially high dimension of parameters, very large number of sums of terms, very large numbers of terms in this sum. And the question is, how do we solve it? This is nonlinear also potentially, so this can be a very, very formidable problem. However, we may be able to exploit the structure of this problem, and the key characteristic here is that it involves a sum of a large number of simpler terms. So let's look at the characteristics of the training problem. Okay, for a nonlinear architecture, this is a non-convex function here with potentially many local minima, and it may be horribly complicated. If you look at it, even for very simple problems, just 2 weights, 2 or 3 weights, plot in your screen, this expression here, and you'll find that it's really very bad looking. You know, it sort of goes flat or going out, dips in, bobs and waves like that, and dips and goes back again. Very, very complicated, really. You can try this with a neural network, very simple neural networks, and you'll see that it's bad. Still, however, people have been able to deal with this. And this is one of those miracles that I cannot explain to you, okay? It has been done because somehow this structure can be addressed with gradient methods. On the other hand, the standard gradient methods would not work for this problem. Why is that? Because to calculate the gradient of the cost function, you need to add the gradients of the individual components. And if there is 10 millions of those, a single gradient is a substantial computation. Similarly, Newton-like methods are even worse, okay? Because then you would need to multiply the gradient with some kind of inverse Hessian, and it's a big mess again. On the other hand, these miraculous methods of incremental versions of gradient methods have worked for neural networks and for nonlinear architectures, not always, okay? But they have worked adequately for many problems. What is an incremental method? Instead of operating on the entire sum at every iteration, it just picks out just one term, okay? And it moves to improve the cost corresponding with this term without regard of the other terms. So it operates on a single term, picks a sample, operates on this term, and it turns out that this has worked well enough for many of the problems that we want to solve. And importantly, there's canned software that you can use, like this TensorFlow, which is a good program that people have found to be successful. If you try to program your own method, you'll see that it may be a challenge. Okay. Okay, now I'm going to switch to another video. Just one moment, please. Okay, so now we're going to go into algorithms, this incremental gradient type of algorithms for sums of differentiable functions. Of sums of differentiable functions, and this is really a problem not in neural network optimization or training of nonlinear architectures. It's more of a nonlinear programming, a generic optimization problem. and I'm going to discuss it to simplify notation. I'm going to discuss it in this form. So instead of looking at my specific regression problem, I'm going to look at the general problem of minimizing f of y. Y here corresponds to the parameters with respect to which I want to optimize. So y is the parameter vector in our context. And the cost function consists of the sum of a number of differentiable functions. And y is n-dimensional. Okay. So what is the ordinary gradient method for solving this problem? It is an iterative method. At the current iterate yk, it generates the next iterate by moving in the direction of the negative gradient. It calculates the gradient of this cost function at the current iterate and moves along the opposite of that with a step size gamma k. So this gamma is a scalar, this is a vector, and this is a scalar, and should be positive. Now, what is this gradient here? Well, it's the sum of the little gradients, the sum of the gradients of the components, right? The gradient of a sum equals the sum of the gradients. So we have here a very large number of components, and this is what makes the gradient method not a little bit unwieldy in this context here. Now here's the incremental gradient counterpart. It chooses just one term, just an index ik that is iteration dependent and moves from yk to yk plus 1 in the direction of the opposite gradient of just that component, just a single component. These two are day and night in terms of overhead. This is far, far cheaper by a factor of m, essentially, relative to that. Now, of course, it's not clear that this will work, okay? We're moving in the direction of some gradient, but this gradient, little gradient, may have no connection with the true gradient, may be very different. So what's going on? Why would this work? Well, here's my explanation to this. This is an example where we want to minimize the sum of quadratic functions of one variable. So each one of these little terms in the sum is a quadratic like that, one of those. So I is the ith term, it corresponds to the ith term, and it's a quadratic in the scalar y, okay? This is a scalar problem. So these are the components of the summation, and if we add them, we get the overall cost function. Now, the overall cost function is something like that. It has a minimum somewhere over here that lies between the maximum and the minimum of the components. Okay. So this region here is interesting. It is the region where these quadratics are minimized. So y stars of I is the minimum of the ith quadratic. And they all lie in some region here. And now we want to minimize this expression. And let's compare the ordinary gradient method with the incremental gradient. Okay, how would the ordinary gradient method work? Okay, the ordinary gradient method operates on the basis of the overall function. So if it starts over to the right, it moves in that direction, towards the minimum. If it starts on the left, it moves in the opposite direction, again towards the minimum. Now the incremental method picks one of those quadratics, and if it happens to be to the right, it moves in the same direction as the ordinary gradient. They would be doing roughly the same things. If it starts on the left, also it will move in the same general direction that the ordinary gradient would do. And at least when we are in this region over here and we approach this area here, we would be doing the right thing, the same thing that the ordinary gradient method would do, even if it calculates the gradients of all the components. So that's the thing. one step of incremental gradient is almost as effective as one step of the full gradient method, which costs you m times more work, okay? So incremental gradient is as fast as the ordinary gradient method with 1 over m the amount of work, provided that I am in this far out region, the blue region, and also this other side, this far out region in the other side. Now, once I get into this red region, which contains the minima of the individual components, the incremental gradient method gets confused. Why is that? Okay, the overall minimum somewhere over here, that's where you want to go. However, if you are over here and you pick this component, for example, then you would be moving away from the minimum. You may even start exactly at the minimum of the overall cost function, but you'd be moving back and forth, depending on which component you pick. Sometimes you'd be picking the right kind of component that would move you towards the global minimum, and other times you would be moving in the other direction. The method gets utterly confused. Okay. So that's the general behavior of these methods. From far out, they are doing the right thing. From the region of confusion, they get confused, and it is possible, however, to make them work, provided you don't make big steps. It turns out that if you use a diminishing step size, a step size that goes to 0 over time, then you'd be getting confused with each step, but you'd be getting confused less. And these confused steps would average out, and overall you would be tending towards the correct global minimum. Okay, for this you require diminishing step size that also diminishes at the right rate, at the right speed. Okay, but there is theory that guarantees this, and the theory is important, but you can see from this example what's the overall trend. It may be that this region is not too big, and even if you get here and you're getting confused a little bit, it doesn't matter to you. Okay, once you're close, that may be close enough. Now, this is a one-dimensional example, but similar things happen for a multidimensional example. You have all these functions whose minima lie in a certain area, this region of confusion. If you're far away, you pick one of those functions, you'd be moving in the right direction as the ordinary gradient. So the dimension here does not matter all that much. You can play with this example with multiple dimensions, with dimension 2 or higher, and you'll see that the same kind of phenomenon can be observed. It turns out that this simple picture captures the behavior of incremental methods. That's what's going on. You'll read analysis about complexity, about all kinds of mathematics, complicated mathematics. But this is the picture that you should pay attention. The other stuff is important, but perhaps not so relevant. Okay, are there any questions here? Let me pause the video and see if there are any questions. Are there any questions? Okay, I'm going to pause it also. That's the third time we're posing for questions. Do you have some questions about this picture, which I think is very insightful? If you study it, you'll find out, you get a pretty good idea of what's going on with these incremental gradient methods. Okay, so we'll keep on going. Okay, we'll keep going. Now, there are variants of this incremental gradient idea. There's a method called incremental aggregated gradient method. In this one aims at acceleration, and instead of using a single term, it evaluates the gradient at a single term at each iteration but it uses multiple gradient terms. Okay, this formula is a little complicated. Note that at the current iterate, we're using the sum of gradients, but these are gradients at the current point, but also the gradients that you calculated at previous points. And we use those to aggregate them, to average them, to obtain some kind of an approximation of the true gradient. So this involves the current gradient of the component, but also the delayed gradients, the previous ones, and we use them as if they were evaluated at the current point. Okay, otherwise it's similar to the non-aggregated method, but both in theory and in practice, this works better, sometimes significantly better. This is a relatively recent development. Incremental gradient methods go way back to the 80s, the late 80s. This is a development that's maybe last 10 years or so. And people have published a lot of theoretical research and also supported the findings of the research empirically, and it is often preferable than the method that uses a single component gradient. It involves more overhead. It involves some memory. It has some drawbacks, but this is a method that is competitive and perhaps better in some situations. Another incremental type method is a so-called stochastic gradient method, also called stochastic gradient descent. Now, this method, stochastic gradient descent, is often applied to deterministic problems, and generally speaking, there is no descent here, okay? So it's often not stochastic, and never it is a descent method. But nonetheless, this name has caught on, and this method is also known by its acronym, SGD, okay? And the method applies not to minimization of a sum of components, but rather minimization of an expected value, okay? So we have a function that depends on the current vector we want to, with respect to which we want to optimize, and a random variable, W. So this is an expected value. You can think of it also as a weighted sum, right? Expected values are weighted sums. So it's not surprising that incremental ideas would apply to minimization of this expected value. And the way it works, at the current iterate, we sample this random variable, and we use the gradient corresponding to the sample, not the expected value, which involves the full sum, but just the gradient of a sample, okay? So this is very similar to the incremental gradient method, and in fact, if you consider the incremental gradient method with a random index selection, okay, this is what we want to minimize, we can convert this to an expected value by viewing the index as a random variable that has a uniform distribution. Then this sum can be written as an expected value, and then the stochastic gradient method is exactly the same as the incremental gradient method. These two are very similar. They have similar analysis, similar behavior. However, this one applies to problems where the random variable is continuous, doesn't have to be discrete. Okay, so it's a little bit more general. Generally speaking, it's not a good idea to take this problem here and view it as an expected value problem here, because you may be able to utilize the fact that this is the sum of a finite number of components. For example, an aggregated method would not apply readily to this formulation here. Okay. So in my mind, incremental and stochastic, they are not the same, although they are closely related. Okay, so these are variants of gradient methods. Okay, let me mention a few issues here, which we're not going to get into. How to pick the step size. Usually the step size is chosen to be diminishing. Gamma is a constant, and with every step, we diminish the step size according to our 1 over k, our 1 plus k plus 1 rate. There are also variants of this. Sometimes, and this is very common in software that you'll encounter, the step size is diminishing for a large number of iterations, and then once it hits a lower bound, it just stays constant after that. This is also called the learning rate, gamma k, and the method that you pick this learning rate is called a learning schedule or something like that. Okay. It's a step size. Step size, a step size rule. And there are several different types, and and there is a lot of analysis around the different step size choices. Remember that the incremental method generally gets confused in a region around the minimum. So how do you deal with that? Is it possible to detect when the method is getting confused and reduce the step size? Okay, that seems like a good idea. And indeed, there are methods that adjust the step size by detecting whether you are in the region of confusion or whether you're not. Yes?
Once you're in the region of confusion, can't you actually put the ordinary gradient method? Like just now you start using the ordinary gradient method instead of step size?
Yeah, you could, but you would still have a problem with the 10 million components, right?
Yeah, but iterations would be less now, right? Instead of...
Right, yeah. Within the region of confusion, the convergence rate of the gradient method with a constant step size, not a diminishing step size, would be faster. That's true. But there is an issue of how do you detect that you are in the region of confusion, okay? That may not be obvious. They require an algorithm, a criterion. Okay, at each step we pick a component on which we iterate. How do we select the order of components? Well, we have a certain number of components, m. We can cycle through them. Start at 1, go to m, and then back to 1. Okay, this is the cyclic rule. And if you know a good order, it may be the best, okay? The best way to operate the method. The alternative is to pick one component at random, okay? Just with a uniform distribution. It's important to use a uniform distribution. Otherwise, there may be biasing, you're biasing the optimization. And there are other possibilities, like you start a cycle and you randomize the order within the cycle. You go through according to this order, and then you go back to the beginning and randomize again, okay? So this is, so within each cycle, you pick all components, but the order by which you pick them changes from one cycle to the next. Okay, there is some theory associated with that, which is kind of interesting. In practice, randomization schemes work better than cyclic schemes if you don't know a good order. If you know a good order, it may be that a cyclic scheme is maybe better. Diagonal scaling. We have a single step size for all components of y, by which we move y, we move according to the gradient, the incremental gradient. We may use a different step size for each component. This would amount to multiplying the incremental gradient with a diagonal matrix, okay? Where along the diagonal we have the different step sizes. There are good ways to do diagonal scaling, and some of the software does that automatically. There are also alternative incremental methods, which are more ambitious and often work much better, but they have not been popular for one reason or another. In general practice, they have not been so popular. Incremental Newton methods, and this is described in your textbook. And the extended Kalman filter, which comes from control theory, has also been used to solve these squares problems. Okay, there's a lot more literature here, and I'll refer you to the references in your textbook. And however, the methods that I have described are the ones that are used most often. Okay, now let's go to neural networks. I described a neural network last time, and we're going to return to this picture again. Now, what's the big advantage of neural networks? They provide a nonlinear architecture that does not use explicit features. you don't need to know good features for your problem. It automatically constructs features for you, and it linearly weighs them. Okay, so what's the structure? I went through it last time, but I'll do it again. We have the state, and then at the end we produce a cost approximation that depends on a set of parameters, the R vector and another vector V. And the structure is as follows. You take the state and you make a first order transformation to put it into a format that is suitable for the neural network. If you know some good features, you can include them here. But this may be sort of scaling, other kinds of transformations. And then you pass this Y vector through a matrix A, which involves, okay, it's a rectangular matrix. It involves a number, the entries of this matrix are adjustable parameters. So part of the parametric form of this neural network is this matrix. This is one set of parameters. And also there's a constant offset B. So in this linear layer, there are parameters given by A and B, essentially a large set of parameters. And at the output, you have a number of scalars that are fed into nonlinearities. This is a single input, single output nonlinearity. So this is a scalar going through here, produces another scalar, and so on. And we obtain these scalars that depend on X, and they depend also on V. And we view this as features, and we weigh them linearly with a parameter vector R. Okay? Each one of these features gets its own weight, and the inner product of R and this feature vector is what we view as cost approximation. So that's the structure. And how do we train this? Well, we train them in the way we discussed. We form training pairs of sample states and sample target costs, beta, and we put all of this together into a nonlinear regression. This is the sum of squared errors. They involve the output of the neural network, and I've written it explicitly. This is the output of the linear layer, and this is the output of the nonlinear layer. And it's weighted with the parameters R. Okay? So this is the structure that you see here. I just written it in this complicated algebraic form. And we compare this with the beta, and we minimize the sum of square errors. So this is a nonlinear cost function, a sum of squares, and we can use the incremental gradient method to do this minimization. And that's the way usually it's done. An incremental gradient method on this thing here, plus perhaps some regularization. Sometimes there's a regularization term that's been added here. And we find the minimum, which gives us the parameters of this linear layer and the parameters of this final linear layer again. And that's our approximation architecture. Now, this neural network, in the literature, neural networks are treated as magical objects, okay? They have magical properties. They can solve just about any problem. It's true that they have been very successful, but the most solid property of neural networks is this property here, the universal approximation property, which says that with a sufficiently rich linear layer and nonlinear layer, you can approximate arbitrarily closely just about any function that you're likely to encounter. This is the universal approximation property. This thing here can be as close as you want to your target function, provided you choose sufficiently many weights here and correspondingly sufficiently many nonlinearities here. That's a solid property and the fundamental result about neural networks, particularly as it relates to our subject. there are other results about neural networks, but they don't relate to our subject here, which deals with cost function approximation. Okay, so what do we use for nonlinearities? The most popular these days is nonlinearities of this form, which are called rectified linear units. Some people call this function here the max function, okay? The positive component of psi, they call it a rectifier. Okay, this rectifier is this function here, and smoothed out. Another name for this function would be a smoothed rectifier with its corner smoothed up in some way, and a popular way to smooth it is using this exponential. If you plot this, you'll see that it's what it shows here. Asymptotically, it approaches on both sides the rectifier, but its corner is smoothed. And we need a smooth nonlinear unit because we want to use gradient methods, and gradient methods require differentiability. So this is something that has come into play for the last, I don't know, relatively recent. In the past, the most popular type of nonlinearities were the so-called sigmoidal nonlinearities, which have this form. They go to asymptotes, they flatten out on either direction. The hyperbolic tangent function is this one here, has a slope of 1 here, and asymptotically goes to 1 and to -1 on the two sides. The logistic function is this. By a translation, gives you something that's pretty similar to the sigmoidal function. Generally speaking, from a theoretical point of view, from the universal approximation property point of view, it doesn't matter which one you use. It just may happen that one type of nonlinearity may work better on your problem than another type. Now, in recent years, there's been a lot of discussion about deep neural networks, because deep neural networks have achieved great success in certain domains. For some problems, they have worked very well. And what is a deep neural network? It's just a shallow neural network replicated many times. Okay, so we have X. It goes through a state encoding layer, and goes through a linear layer, and then through a nonlinear layer. And over here, instead of going straight out and pick up those features and linearly weigh them, we use them as input to another linear layer, which the output of which is fed into another nonlinear layer, and so on. And you can have quite a few nonlinear layers. You can have in the tens, okay? In the old days, people were using just a single layer or maybe 2 layers, very seldom more than 2, like 3, okay? There were reports of people having tried more layers, but nowadays, these are more popular and have a lot of success to show in certain domains. Why is this true? Well, people don't quite understand, but people speculate about why deep neural networks may perform better. They don't always perform better, but you may try them and you may find great improvement. Well, a multi-layer network provides a hierarchy of features. Instead of just single features at the end of the first nonlinear layer, it gets a set of features here, which is used as inputs to produce a new set of features, and then a new set of features. So we have features on top of features, building on top of features, and that creates a richer set of nonlinearities in some sense. Some of the early features may capture some gross effects that may be refined by subsequent layers. I can only speculate about that, and it's not very clear, but that's one common explanation that people use, that people give for the success of this network. Another possibility here is to make this layer specialized, like the matrices here may involve special structure which focus on particular characteristics of the target function. So special linear operations such as convolution can be built in here. This is popular in image processing. With convolution, you can sort of focus on particular types of objects in your image. And the upshot of all this is that if you're able to design this deep neural network and specialize it to your problem, then it may become easier to solve this training problem because the number of parameters in the linear layers may be drastically decreased. In other words, if you use 10 layers here, you may need overall fewer parameters than if we were to use a single layer with many, many parameters. Because this is more sophisticated, basically. So they have been found to be more effective than shallow neural networks for some problems, not for all problems. For example, I've mentioned in past lectures the backgammon program of Tesoro, which uses a neural network. And in the internet, you'll find descendants of the backgammon program of Tesoro that use neural networks, but people have tried many layers, and it didn't make a difference. Tesoro himself tried several layers, but he ended up using two layers. And in fact, he found little difference between using a single nonlinear layer versus using two. Nowadays, backgammon programs use 2 layers, okay? That's not because of lack of trying with more layers. Okay, now one thing about deep neural networks is in order to use the incremental gradient method, which is still the most popular, you have to calculate gradients that propagate through, all the way through this complicated structure. How do you calculate these gradients? Well, with a single layer, it's pretty straightforward to calculate the gradient with respect to the parameters, but here you have this concatenation of layers, this composition of functions, and you have to use the chain rule to calculate the gradients with respect to the parameters of each one of those. And there is a clever algorithm, a clever way to use the chain rule called backpropagation, which gives you the gradient of this thing here, or rather least squares term, with respect to the parameters of the layers. So backpropagation, that's what backpropagation is. It's just an intelligent way to use the chain rule to calculate the incremental gradient of each component term at every iteration. And your textbook has a derivation of the formulas for the incremental gradients, and you may want to read that or the other ways of explaining this backpropagation rule, but it's just the chain rule of calculus. Okay, so here we are with neural networks. This is the one-layer network. The idea is to generate features. Incremental gradients are used. Universal approximation property holds. There are several different kinds of nonlinearities. And there are deep versions for which also the universal approximation property holds. But why is it that indeed neural networks have this capability? Why is it that by stacking up a lot of parameters, you can approximate any function that you might be interested in? So my challenge question to you is this, okay? Let's look at how neural networks generate features. And I'm going to look at a single variable problem, a one-dimensional state, x. If you pass through a linear function, then from x, it becomes this function here. It involves a different slope gamma and a horizontal shift to beta. So if you pass x through a linear layer and then rectify that, then you are going to get this red function. Okay? So let's view this as a fundamental operation. And my question to you is, how can we use linear units and rectifier units to construct another feature vector, this feature vector, whereby you input x and at the output you get this function. Okay? So I want you to think of how you can use units like this to produce a pulse type of feature. And let's ask also the question, since you have this capability, what are the kind of features that can be produced by neural networks, at least in the scalar case, scalar X that I have here? And then go even further, why do neural networks have a universal approximation property? Okay, guys, this was a long clip and a lot of material to digest. We're going to take a break for 15 minutes, okay? We'll come back in 15 minutes. And then I'm going to discuss this, this question. And it would be also a good opportunity to ask your own questions. But if there are some questions right now that you want to ask, why don't you bring them up?
I saw on the slides that you had engineered features being included with the learned features at the final layer in the network. To your knowledge, do you know of any sophisticated means other than concatenation that have traditionally been used to accomplish that combination of features?
Okay, I had engineered features, you mean, and learned features, learned through the neural network. But in my diagram, like for example, I hope you can see my screen. In my diagram here, in this encoding, we can, this encoding produces both, includes engineered features, what you call engineered features. So,
Right.
But we don't add them at the end, okay? We could have added them at the end, but not in this figure.
I see.
It's possible to pass them straight through to the linear layer, if you wish. And okay, I mean, that's a plausible approach. I don't see anything wrong with it. Does this answer your question?
I think so. Yeah, I was talking about combining two channels basically. And then I don't know if you've come across that very often. I've seen concatenation used to do that. I didn't know if there was other more sophisticated methodologies for doing that. But
You can introduce engineered features anywhere in here. It's not going to hurt you, but it's going to complicate things perhaps with little effect.
I see.
And I'm sure that people have tried all sorts of schemes within the structure. Mm-hmm. And I'm not familiar with the entire literature, which is vast, like I said. But if you look around, I'm sure you'll find a variety of schemes along this around this figure here.
Cool. Thank you.
Okay, so in 15 minutes, let's get back, and we're going to take up this question and then discuss additional issues regarding neural networks and training. Okay, guys, we should be getting back to our lecture. Can you hear me?
Yes, yes.
Okay. So, and you're seeing my screen, right, where I'm pointing now?
Yes.
This slide, okay. So I want to address this challenge question, okay? How can we, with a linear layer and followed by a rectifier, producing the simple function, construct more complicated features like the pulse feature here, which we can use? We can concatenate several of those, and we can have features that are more complicated. But before I get into that, are there any questions about the previous part of the lecture? Okay, so I'm going to now get this part of the video. Okay. We take X and feed it into two different linear blocks that are followed by a rectifier. And these blocks have parameter, the same slope, but a parameter beta 1 for the top and beta 2 for the bottom. So and then you subtract them at the output. Okay, you multiply them with +1 and -1. And then what you get is this thing here, and then at beta 2, the other one kicks in and flattens the slope. So with 2 linear blocks, I can construct a feature like that. And now if I take this one and take another one, shift it to beta 3 and beta 4, like so, I'm going to construct this pulse feature. Okay, let's go through this again. X goes through a linear layer that consists of 4 units here, with parameters beta 1, beta 2, beta 3, beta 4, and a common slope. I mean, you can play with the slope, but I have it a common slope here for simplicity. The outputs of this linear layer are fed through rectifiers. And what we get is from the first 2, we get this, plus minus. And then from the bottom 2, we get the opposite, which are subtracted, multiplied with +1s and -1s appropriately, and then you get this function here. So it is possible with a linear layer and this nonlinear rectifier layer to construct this fundamental feature. Now, if I have this fundamental feature, how would I construct more complicated features? We take this one, and we have some more stuff here that constructs another feature. Okay? And moreover, I can multiply the output of this and make this pulse higher than the other pulse, and then have some negative pulses too. So I can construct essentially any piecewise constant approximation as a feature. Now, if I have the piecewise constant, by making the width of the pulses narrower and narrower, I can approximate as closely as I want just about any function. Okay? What would that mean? That would mean that to cover a certain area here, I would need a richer linear layer and corresponding nonlinear layer. I would need to stack more of those. Now, that's not the way the neural network works, okay? But it is a proof that it is capable of producing arbitrarily complicated features. In practice, you'll optimize the parameters so that you can get even better approximations. But the universal approximation property says simply that the neural network is capable of approximating any function, and by optimization, it can do it better. Of course, if the rectifier was a linear unit, an RLU, a rectified linear unit, then you would have some smoothing out of these corners, smoothing out here too, and but it doesn't make much difference, okay? By making the pulses sufficiently narrow and the slope sufficiently high, you can still get all the as adequate approximation as you may need. Yes.
So this is exactly how you generate a square wave using electronic circuits, which is why these units are called rectifiers.
You can make a what?
So using a triangular wave and a rectifier circuit, this is exactly the way you generate a square wave.
Okay, perhaps that's where the rectifier name comes from. Yeah, yeah. I'm not quite sure where it comes, but I know it has an origin. Yeah, yeah, yeah. Yeah, so they use for image representation. They use superposition of fundamental blocks like that, pulses, right?
I'm talking about electrical currents to generate square signals in electronic circuits.
Okay, maybe you can explain to me at the end. Okay. Let's go into our final topic for today. We have these neural networks that can do cost function approximation and can be trained with incremental gradient methods and other methods. How do we use them in dynamic programming? In finite horizon dynamic programming. Remember, in dynamic programming, start at the end and construct cost function approximations. Well, we can do it step by step by using a neural network for each stage, generate data using the preceding neural network, and then to build a neural network for the current stage, and then use data from that neural network to go one stage back, and so on. So here is the algorithm. This is also called fitted value iteration. And it does dynamic programming approximation sequentially going backwards. We start with the terminal cost function, and then using this cost to go approximation, which may be constructed by using a neural network or a linear feature-based architecture, we use one step look ahead to construct a data set consisting of state cost pairs. So we want to approximate this expression here, right? The dynamic programming expression. So we pick a large sample of states, xks, where is q of them. Q can be very large. And we calculate this expression here using j tilde from the preceding stage. Okay? So for just the states in my sample set, I do this minimization, this expectation. Of course, this involves quite a bit of computation, but let's suppose you can do it, or you can do it approximately, and you can get this beta case of S. So this is my data, and then we train an architecture for j tilde k. Using j tilde k plus 1, we get an architecture j tilde k by solving this least squares problem. So I have this data, I put it into this least squares problem, and I solve this minimization by some form of training algorithm, be it incremental gradient or be it an exact calculation in the case of a linear architecture, and so on. This is very simple and very straightforward. One neural network or one approximation at each stage, and we use the one at time k plus 1 to form an approximation at time k. And we go backwards, and we obtain these approximations, and by minimization, in one step look ahead, we can get a policy, an approximation to the policy. So what do you see that bothers you here, perhaps? What's kind of bothersome here?
The approximation error keeps propagating.
The approximation may be propagating. So it may be bad after a few iterations and may keep getting worse. Indeed, this is true. And this method has serious problems for long horizons. For example, in infinite horizon problems, this method has been suggested. But it turns out that and we'll give examples of that, it can go unstable. Even for very simple cases, it can just go unstable with the approximation having errors that grow over time. Okay, so that's one potential problem. But if you have a finite horizon problem, this may not show. What other difficulties do you see here?
It's a lot of computation.
A lot of computation. Why?
I mean, you train neural nets for every state.
Yeah, I may have 100,000 states here. And that means that for each one of those, I have to form this expectation, which may be a substantial computation. And moreover, I have to minimize overall controls. So it's okay. So maybe I have reduced the amount of computation, the number of times I minimize an expectation, but still it may be very large. Okay. Yeah, that's a major problem. Of course, it may be that you're lucky and you have an easy problem for which this is possible. Okay, so how are we going to circumvent this? Well, here's where Q factors can come into play. Okay, we have talked about approximating cost functions, but Q factors are also cost functions. They are the costs of state action pairs. Okay, so we might as well approximate Q factors and do the same thing, go backwards starting from the end. So this is what this is. This slide is about sequential Q factor approximation. Now, the basic Q factor equation is this. Ordinarily, you would have the optimal Q factor here to generate the optimal Q factor of the preceding stage. However, suppose you approximate at the end, and then you go backwards, and you generate a sequence of approximations which are parametric. There's a parameter vector for each stage. So you do this, you go backwards starting from the end, and first determine an approximation. You determine Rn minus 1, okay, at the next to last stage, and then use that to determine a set of parameters for stage n minus 2, and so on. Okay, now this involves also an expectation, and involves also a minimization. But there's a nice thing here, okay? The order of expectation and minimization has been reversed. So that means that instead of finding the expected value of this expression, I can just sample it. I can just use samples of WK to put together into my least square sum. That's a key mathematical idea in Q learning, using Q factors. That minimization of expectation cannot be sampled easily, but expectation of minimization can be sampled. That's the trick. So specifically, we obtain this thing here, the parameters Rk, by training with many pairs, sample state action pairs, and corresponding samples of the approximate Q factor. And that sample need not include a full expectation, maybe just a sample value corresponding to a sample value of the corresponding random variable. In fact, I can do all these calculations without a model. It is sufficient to have a simulator that generates, for every state control pair, it generates the cost and the next state. That's all you need to implement these calculations here. So a simulator will work, and you don't need to have a model in the sense of, you don't need to have the probability distributions of WK here, explicit analytical formulas for that. The simulator to generate samples is sufficient. So this is a model-free algorithm, and it may involve neural networks, or it may involve linear feature-based architectures. And after you have done this training backwards, and you have obtained these parameter vectors for each stage, then you can implement a one-step look-ahead control by minimizing over Q factors. So here, for every possible control, you have your approximation architecture generate a value, and you pick the control that is minimum. No model needed again for this. The neural network or the approximation architecture generates these Q values, and you do just a minimization either by brute force or by some kind of other, in some other way, perhaps involving some optimization. This is approximation in value space again, okay? And it is model-free for finite horizon. We will see the analog of this also in an infinite horizon. And again, it's this reversal of order that plays the fundamental role in why these things work. Another thing to note here is that to calculate online the control to be applied, you have to minimize over these Q factors. You don't have to do this, okay, the standard minimization that involves forming like expectation and so on. Okay, so we have one more video clip. Are there any questions? Okay. Can you see my screen properly?
Yes, looks good.
Okay. Are there any questions so far? I have one more slide on deep neural networks. There is a mystery around them, and there has been some significant progress in understanding why they work, and this slide is about that. So let me get started. Sort of a mystery for a number of years. People knew about the advantages of deep neural networks, or at least suspected them, in starting about 10 years ago, but there was literature even 20 years ago that that indicated that with a richer network, more parameters, you could get better results. Well, in the last 2 or 3 years, there's been some intensive research that has been done, and I'd like to bring you up to date a little bit. Even though there has been a lot of speculation, I mentioned the reasons why people thought that deep neural networks work better, like richer features, hierarchy of features, and so on. People have now focused on the over-parameterization. The capability that these networks have many parameters, many more parameters than data, okay? More parameters that you really need to capture the data. And it is generally thought that the ratio of number of weights to number of data points affects the quality of the training architecture. Now, if this ratio is close to 1, in other words, if you have a number of weights that's about the same order of magnitude as the number of data points, then what will happen through the training process is that the architecture will tend to fit very well the training data. Now, in machine learning, there's a phenomenon that's called overfitting. It's something to avoid, because if you specialize the architecture to the data, then when new states come outside the data set, you may do very poorly. So this is a well-known phenomenon to avoid in machine learning. Avoid having this R close to 1. However, it turns out that for R considerably larger than 1, then this problem of overfitting can be largely overcome. In theory, and also in practice, with some tricks that people have figured out. So this is the latest word on research for deep neural networks, and indeed it's quite revolutionary. It's a quite revolutionary insight, because it brings the entire machine learning field on its head. People were thinking that take R less than 1, significantly less than 1, and now people are saying take R significantly more than 1. Okay, and moreover, use deep neural networks, because then naturally you get more weights than data points. So that's where it's at. And there's a lot of recent literature. And in fact, just this last month, there was a textbook that came out on the internet that's freely available by Hart and Recht, and talks about a number of issues around classification, pattern recognition, reinforcement learning, and also the issues of training. So I'm going to leave this here, and I'm going to go into my next slide. Are there any questions, by the way? Okay, here's another issue that's important. Why do we train? Why do we construct cost approximation, Q-factor approximations? We do it in order to compute controls online by approximation in value space. On the other hand, to compare controls at a state X, we don't need it is sufficient to have the Q-factor differences. In other words, if this difference is positive, that says that U prime is better than U. And if you are interested in finding the optimal U, it's sufficient to have the differences of Q factors. Whether you have Q factors or Q factor differences, you're going to get the same result. But what happens to training in this light? Okay, here's an example that's kind of discouraging and points the need to some remedy. Consider a system that has this form. It's a scalar system. Delta is a very small positive parameter. Think of this system as discretization of a continuous time system, of this continuous time system. X dot equals U. We went through this system in the context of the oversimplified adaptive control, the cruise control problem. And let's take a quadratic cost function. Now, if you discretize a problem that's continuous time and delta is the discretization parameter, then the cost of a stage is proportional to delta, okay? Between time t and time t plus delta, the cost that you pay is very small, and it's proportional to delta. So this system is a simple one, but very typical of those that result from discretization of continuous time problems. So now let's consider a policy, mu sub x equals minus 2 sub x, a linear policy, like you would expect the optimal policy to be linear for this problem. And this is a stable policy, a nice stable policy, and because delta is small, right? So it's stable. Now, if we do the Riccati equation calculations that you have gone through in homework and we have done in class, you can calculate the cost function of this policy, J mu. J mu is quadratic in X, remember? And the exact form is what you see here. And there are also some extra terms of delta squared. So it's this, okay, it's still quadratic, but the remaining terms are insignificant relative to this because they're second order in delta. You can also calculate the Q factor of this policy. And the Q factor has this form. Okay, this requires some calculation, but trust me, this is the correct formula. And it is quadratic in X and in U, and it involves delta. But what's significant here is that the terms that involve U are multiplied by delta, and they are insignificant relative to the terms that involving X. So the important part from the point of view of policy improvement, remember that we minimize this expression here. Suppose we try to improve mu through our rollout, we use mu as a base policy, and we minimize here. Okay, that's fine if we use the exact calculation. However, when we take this Q factor and we approximate it with a Q tilde approximation architecture, like with a neural network, the neural network is going to try to mimic this part. It's going to wash out, neglect, essentially, nip in the bud, this part here, because it's just noise relative to this. So when we make an approximation of this Q factor, then the approximation is going to be dominated by this part here, and the important part, which is this, the red part, is going to be lost. So the method is going to fail utterly. Now, what is the remedy for this? Well, it goes back to the question I've asked here at the top. Do we use cost? Do we approximate Q factors or Q factor differences? If we take this Q factor difference, this term here, which bothers us, which is disproportional to the rest, is going to be subtracted out. So it's not going to play at all. And what we're going to have is terms that are proportional to delta, which are comparable, and there's no problem in that case. Now, people have played a lot with this idea here of using Q factor differences from the early days of reinforcement learning. There's a methodology called advantage updating, which argues for approximating Q factor differences as opposed to Q factors themselves. Okay, so now let me take the same question and bring it to a more general context. Suppose you have Q factor calculations that include disproportionate terms, terms that can throw off any kind of approximation architecture, approximations with a neural network, for example. So what would be the remedy to this? The remedy is to subtract some state-dependent constants from the Q factors. These are called baselines in the reinforcement literature. And these constants are going to wipe off the offending terms, the terms that give us trouble. So how do you pick the baselines? Well, I gave you one possibility in the previous slide, but there are others. These baselines are a concern in a number of contexts in reinforcement learning, and you will encounter them in the literature. And their purpose is to deal with disproportional terms coming in approximating Q factors. Here's an example. Suppose that we have a base policy, mu, and we want to do rollout with cost function approximation, J tilde, that approximates J mu. So the rollout includes, it consists of minimization over U of this expression at a given state X. How do we deal with this G term, the cost term, being tiny relative to this cost here? This is the cost of a stage. This is a cost of many stages. So this is likely to be considerably more than this, more sizable. So if you add approximation error to J tilde, this approximation error may wipe out completely the effect of this first stage cost. And this happens typically in the case where you have a continuous time system and you discretize it. This is going to be proportional to delta, the discretization interval, whereas this one is going to be substantial. Now, one remedy to this, which was also known since the early days of reinforcement learning, particularly in control theory, on the control theory side of the methodology, is what you do is you subtract Jx from this and you form the difference of future costs to go from X to this state here. And that makes the corresponding difference term comparable to the first stage term. And then that sort of corrects the problem to a great extent. Now, all of this is in your class notes in section 2.3. We haven't covered it before in class, but it's in the class notes and you can see the details there. Okay, here's another possibility. Instead of learning or approximating J mu of X, we may try to learn directly cost function differences, okay? J mu's of X and J mu's of X prime. So that requires training where the input is not just X, but pairs of states. It turns out that you can do that. And then you can use these differences in this expression here and sort of emulate the process that I have described. This is known as differential training, and there is literature on this. Not very widely known, but I think it's an interesting possibility. Finally, I mentioned advantage updating, which relates to the previous slide, which is to work with relative Q factors. In other words, construct as a state-dependent baseline the minimum Q factor from Q's of XU. And that sort of brings the Q factors subtracts out constant terms that are disproportionate. Okay, so I'm going to stop here. This is my last slide. Are there any questions? Okay, well, that was the last slide of this lecture. Are there any questions on this issue of Q factor differences, advantage updating, baselines, and so on? All of this is very important in practice.
Quick question. So are there any like relative advantages and disadvantages between these different methods? Or is the Q factor difference usually the best way to go about solving it?
Okay, which methods are you referring to? The methods involving baselines?
So yeah, the baseline
training.
versus, yes.
Well, baselines arise in reinforcement learning in several different contexts. Advantage updating is very well known, goes back to the 90s, early 90s. It has been tried. It's generally considered advantageous, in fact, critically important in some applications. Typically, these applications involve disproportional terms in the Q factor calculations, like you see here. Differential training, which is actually my research, has not been picked up. I think it is interesting, but people have not worked on it. I think they're scared of the possibility of training cost function differences because it requires twice as big input to neural networks. I think it's possible, but it has not been picked up by too many others. Some, but not too many.
Thank you.
Baselines are also used in other calculations, which similarly involve disproportional terms and fitting with neural networks and other architectures. For example, in policy gradient methods, it's very common to use baselines. Now, we haven't gone into policy gradient methods, but perhaps we'll mention baselines within that context when we get there.
Thank you.
Okay, the last slide about the next lecture. We are going to cover infinite horizon theory and algorithms. We're going to revisit discounted and stochastic shortest path problems in greater detail. We're going to discuss some of the theoretical and algorithmic convergence issues of methods such as policy iteration. Our objective is to go into training issues in the context of infinite horizon. Because if you want to implement approximate policy iteration for infinite horizon problems, you need to do offline training. Remember, the rollout is just a single policy iteration. If you want to use multiple policy iterations, like in AlphaZero, for example, to construct more sophisticated policies for approximation value space and for cost function approximation, then you need to go into policy iteration, and there are special issues that arise within that context. That's 2 lectures from today, okay? In the next lecture, we're going to cover just the theory, just background and support for what's coming in 2 lectures from now, which would be approximate policy iteration. Now, all of this is available in the video lectures and the slides that are online. So if you want to read ahead and watch ahead the video lectures, it's possible. All of this material you can find at the website of the course. So that's all for today. Are there any questions? Let me repeat my plea again to think about your project or term paper. And next week is spring break. At the end of spring break, I'm expecting from you a 1-page description, 1 page or less description of what you plan to do. And I want to make sure that you are on the right track. And please attend to that. And I'll be looking forward to see your proposals. So that's it for today. And we'll see you 2 weeks from now.